In this video, we're going to look at organic chemistry. And what is organic chemistry? Well, it's the study of carbon-containing compounds and their properties. So it's all about carbon. Inorganic chemistry, which is another branch, is kind of every other chemical that you've probably seen that is not alive. So we're looking at living, organic, carbon things for inorganic chemistry. So what's special about carbon? Well, it's found in group 4, which means that it needs to form 4 bonds to become stable. So it's all about the number 4. And what we're going to be doing a lot here is we're going to use hydrogen, because hydrogen is able to come along and nicely fill one of those 4 bonds with the carbons. They can fill all 4, they can fill 3, 2, or 1, whatever they're going to do. Hydrogen is very helpful. So what are hydrocarbons used for, and what are they? Firstly, that just by the name may insinuate, hydro meaning hydrogen, carbon meaning carbon. So these hydrocarbons are compounds that contain only hydrogen and carbon, and they are used every day as fuels like gasoline. So hydrocarbons. So there's a couple of branches that we're going to be exploring in the first couple of lessons. Firstly, we're going to look at alkanes, which have single bonds. Then we're going to look at alkenes that have a double bond. And then we're going to look at alkynes that have triple bonds. And all these hydrocarbons can be found as either a straight chain or they can be found as some kind of ring. And we'll investigate both of those as well. So let's start with the alkanes, the compounds that have single bonded carbon-carbon. And so this is just the way I like to do it, showing that 2 carbons have bonded together. So any hydrocarbon containing only single bonds can also be known as a saturated hydrocarbon. So if you hear me say the word saturated, I'm talking about a hydrocarbon with single bonds. So probably the easiest thing to do is to talk about the first 10 alkanes here. So I want you to pause the video and create this table. Leave yourself enough space in the drawing column. And now we're going to fill this in. So we're going to start with the simplest one here, which is made of 1 carbon. Would just look like this. And so we'll draw our carbon, we'll draw our 4 bonds, and then we're going to put hydrogens at the end of each of those bonds to make the molecule stable. There's kind of no condensed drawing of this one, or it might look exactly like the general formula, which is CH4. Now these are alkanes, so all of our endings are going to end in ane. And when you see something with 1 carbon today, we're going to have to remember the prefix is meth. So remember, meth means 1. That's going to come up again later. If we're looking at the next one, it's got 2 carbons. So what I like to do is draw those 2 carbons, bond them together, and then go about adding my hydrogens in. When we condense, looks a little something like this. So this CH3 would represent those carbons and hydrogens, and then the CH3 would represent those carbon and hydrogens. And we can just condense it all together to give us our C2H6 formula, which is now called ethane. So we drop the M, so F. F means 2 carbons. Something with 3 carbons, we'll just draw this one. And then we'll go ahead and write our condensed right beside it. And there's our general formula. And for King of the Hill fans, Hank's favorite gas is propane. We're only going to draw a couple more because it's going to start to get very repetitive here. So we've got 4 carbons. It looks a little like that. Condense it out. There's your general formula. And this one has a unique name. This is called butane. And when we start to get to the 5th one, which is pentane, all we're really doing is we're just adding another one of these CH2 units in the middle every time. It's just getting bigger. You might even notice that our carbons are always going up by 1 and our hydrogens are going up by 2. Now this one's named pentane. Now the rest of these ones after this all sort of follow the conventional shape prefixes that we've seen before. Again, feel free to pause the video and get this jotted down. Once you got that down, here is pretty much the rest that we need to know. We already drew these ones here, so make sure you get hexane and its formula, heptane, octane, nonane, and decane written down. And while you're doing that, you might notice that there's this weird thing at the bottom here. This just helps you figure out the formula. So if you say you took the number 10 and you plugged it in for the N, you'd get 10 carbons. Then you put the 10 in over there, and it would tell you that you have 22 hydrogens, and that would give the formula of decane. C10H22. It's kind of handy. Anyway, knowing this, we can now tackle a few questions. So let's name the following. So if you're going to name the following, what I would do is I would simply draw over and count how many carbons I'm drawing over here. I drew over 8. That means this one is octane. And I draw my hydrogens in, and I'm done. Octane. Now the other version of a question we can do right now is we could draw the following. So what if I said draw hexane? Well, you'd say to yourself, okay, it's got hex is 6, so I'm going to draw 6 carbons like that. And then I'm going to start to put my hydrogens in. So here's a little bit of a short form. Looking just briefly back at our earlier example, this N carbon actually ends up having 3 hydrogens around it. So when I go to do that, I can draw all the hydrogens out, or I could just put H3. Done. Now any of these middle units are going to have 2 hydrogens, so I can put H2 there, H2 there, H2 there, H2 there, and then again we're at an N carbon, so it's got 3 hydrogens. So that's kind of our condensed version. Now I don't care if you draw them like this till you're good. Eventually it might be a little faster to move on to this, but whichever method works for you, and do it. It's fine. So continuing on here, now that we've got some knowledge, I want to talk about something called an isomer, or isomers. These are compounds with the same general formula, but are drawn differently, unless they have different properties. They're different compounds. I want to explore this through an example here. So draw CH10 as many different ways as possible. Now when you see that, you should say to yourself, okay, C4 means butane, so that's probably the first one we're going to draw. And if you count up the hydrogens, there are 10 hydrogens. And you're right, we've got butane. But there's actually another way for us to connect up the carbons. So the first thing we could do is we could draw 3 carbons in a row, and then we could take that 4th carbon, instead of sticking it on the ends, we could stick it pointing up, or it could point down. It's kind of the same thing. So we've actually connected these in a different way. Once you've done that, you can go ahead and put your hydrogens in, like so, and count them up, and sure enough we do have 10 hydrogens, so both formulas are C4H10. The problem is that whereas this chain was 4 long to call it a butane, this other chain that we drew is only 3 long. It could be 3 that way, you could actually sort of come up with 3 that way. Any way you can see 3 that way. There's many different ways. The fact is when you get 3 carbons in a row, you can't call it a butane anymore, you have to call it a propane. So if we just, let's say for example, we just said that that was going to be our carbon chain, we've actually still got to name this CH3 group that's now coming off this chain. So we need to talk about this because this is something new. This is what we call a substituent group. So we're going to draw another chart here. Let's call this one the substituent group chart. It's going to be shorter than the last one, and these are groups of carbons connected to our main chain. Again, we'll start with one that has 1. This is the one we just kind of saw. Looks a little something like that. You can put your hydrogens in, and here is where it would bond to the parent chain. Now there isn't really a condensed, kind of the, the general formula and condensed are sort of the same thing. Perhaps I should have just put them together. Anyway, if you've got a CH3 unit, you're going to call it a methyl. Now notice our ending has changed. It's now YL. This stands for a methyl version. Not methane. Methane would be a complete molecule. Methyl is an incomplete molecule. It's going to attach to another molecule to become complete. So how about, let's go on to our second one here. It looks a little something like that. Again, you put your hydrogens on. And we can draw a condensed like that. And there's our general formula. Either of these are going to be acceptable when you draw a molecule. And just like before we saw ethane, now we have an ethyl. And when it comes to 3, it looks a little something like that. Now, again, we're just starting to add this extra CH2 unit in every time. Our general formula goes up by 1 carbon and 2 hydrogens. You'll notice our general formula is not quite the same as our previous general formula. We've lost a hydrogen in each example. Anyway, this one's propyl. And so we're just going to carry on with butyl, pentyl, etc., all the way up to decyl. You're mainly going to come across these ones, though, in part of today's lesson anyway. So if we jump back to this example and we want to name this one properly, we said that that was our propane, and then this is our methyl group. And it's important we tell the reader which carbon this is on, because it's like this is the first carbon, that's our second carbon, that's our third carbon. We got a methyl group hanging off the second carbon, so we could call this a 2-methyl propane. Some people would also just say it's a methylpropane. We don't need to put the 2 because there's only one place to put that methyl group, and it was on the metal carbon, whether it pointed up or pointed down. That was the only place to put it. So you could call it a methylpropane. So I want to talk about some rules now that we've just come across for naming these branched chain alkanes. So the first thing we're always going to do is we're going to name the longest chain. So take your pen or pencil, draw on your piece of paper, and all the ones you've drawn over make your longest chain. This is also called the parent chain. Number 2, we're going to number the chain so the subgroups have the lowest number possible. We haven't really come across this lowest number possible, but we want to number our chain so we get these subgroups to have lowest numbers. Let's investigate an example, and we're going to come back and we're going to end up with 5 rules. So give yourself some space on your paper as you copy these down. Okay, so let's name the following. I haven't drawn in all the hydrogens. I'm going to do that last. I just wanted to make this clear here. So rule 1 says we want to draw on our longest chain. So there's actually a couple of different ways we could have a longest chain of what looks to be 4. You could have 4 there, or if I change colors, you could go and down. Either way produce 4. Good news is either way are going to produce the same answer. So why don't we just stick with the blue one, which is straight across. Okay, so we're going to call this, what do we call 4 carbons straight across? We call it a butane. Now we need to identify this group. This is a methyl group, and methyl. That didn't work out. There we go, methyl. And what carbon is it on? Well, let's count this here. If we went this direction, 1, 2, 3, we could say it's on the 3 or 3rd carbon. But I guess the problem is that we always want to have the lowest number possible. So if we actually numbered right to left, this would be 1 and this would be 2. So we actually have a methyl group on the 2nd carbon. We're going to call this a 2-methyl. And again, just like the previous example, we don't actually need the 2 because, well, there's my hydrogens. There we go. And there's that molecule, it's just backwards. So we don't really need the 2 because I can move this methyl group to different sites on the carbon chain, like there. So I just moved it up to that spot. It's still the same molecule, I just flipped it around. Now I just flipped it down, so now it's pointing down, still the same molecule. Even in that position there, that methyl group is still, they're all the same molecule. That's kind of my point here. So there's only one way to draw this one. So we don't actually need that 2. We could just draw it as methyl butane. If you put the 2 as a beginner, I probably wouldn't mark it wrong. But in upper levels, they might want you to recognize that there's only one version of these molecules, and so you don't need that 2. But most of the time, we're going to need the numbers. Very few times we won't. All right, so let's take a look at another example here, and we're going to have a new rule coming. So first things first is we're going to do our longest chain. And longest chain could be across like that. There's actually a second way we could do it. We could go down and across, but I'm not going to go with that. I'm going to go with our first one. So in orange, you color over this, and you say, okay, there were 5 there. That is a pentane. Now let's look at the groups here. Got a subgroup there and a subgroup there, and they are both methyl groups. And here's where we're going to number our chain. Hopefully, again, it looks obvious to you that we've got something on, if we number it this way, we'll have a methyl group on the 2nd carbon right there, and a methyl on the 3rd carbon. So here's how we write that. We write 2, 3. This is going to be one of our new rules, is that you separate numbers with commas. And then we need to say methyl. Now, there's a bit of overkill at this point. Because there are 2 methyl groups, we have to say dimethyl. The di, to me, really, it's kind of like, I know there are 2 methyl groups because there are 2 numbers. But the way to do it properly is you put a prefix in front. So if there were 3 methyl groups on this molecule, you'd say tri. If there were 4, you'd say tetra, and kind of so on here. Now, why are these numbers necessary? Well, look at this example. It's almost identical. All we've done is we've moved that methyl group that was on the 2nd, we moved it over to the 3rd. So we get this molecule here. It's still a pentane, 5 across, and we still have 2 methyl groups, but what's happened is they're both now occurring on the 3rd carbon, so I'd actually need a couple of 3's, 3, 3, dimethyl. So both of these compounds would be considered isomers of each other, and hopefully this shows you why you need to put the numbers in. You need to tell the reader, well, what carbon are they on? In this first example, the one was on the 2, one was on the 3, and then in this example here, we had them both on the 3rd carbon, so the dimethyl. So let's add that to our rules. Separate numbers with a comma. I guess I didn't make a big deal of this, but we also want to separate words and numbers with a dash. All right, another example here. Let's get our longest chain. Again, there's a couple of ways to do this longest chain, but I set this one up so we can just go straight across here. So that's 1, 2, 3, 4, 5, 6, 7 carbons. We're going to call this a heptane. Now we need to identify our substituent groups. So this is all of one group. It's got 2 carbons, it's got 5 hydrogens. This is actually an ethyl group. Now, on this end of the molecule, we have 2 other substituent groups. They're separated. They're both CH3s, and hopefully you recognize these as being methyl groups. So we have a couple of methyl groups in this example, and we have an ethyl group. Now the question becomes, which do we put first? And what we want to do is we want to alphabetically organize these. So we want to get these in alphabetical order. That's going to be our 5th rule. So if I number my chain, I get a 1, I get a 2, I get a 3, I get an alpha group on the 4th carbon, so 4-ethyl. And now what I'm going to do is my methyl groups are both on the 2. So I'm going to call this a dash 2, comma 2. They're both on the 2nd carbon, dimethyl. Now I do want to point something out that I did say that this was going to be in alphabetical order. And if you look, E, and then because we added that prefix, actually there's a dash, don't put that dash, I don't know why that's there. Scribble that dash out. Words can all go together like that. That's all one word. Dashes only go, actually the dash should have been right there. There we go, correct these on the fly. So 2, 2 dash dimethyl heptane. So we put the D in for di. That sort of made it alphabetically ahead of the ethyl, but we actually want to ignore the prefixes when we go to name these things. So don't worry about that di. Again, when you get them in alphabetical order, you got your ethyl before your methyl, and this is going to be our 5th rule. So rule number 5. Organize subgroups in alphabetical order, ignoring the prefixes, and I listed 6 prefixes. I just ran out of space. I would have done the rest of them. Okay, so now I want you to complete sheet 1 and check your answers. The front of that sheet is very important. I want you to be careful identifying the parent chain. Let me just show you a couple of tricks that can happen. So for this first example, some students look at this and say, okay, I see 4 across. I'm going to call this a butane. Well, the fact is that the chains are bent up. This is not 4, it's actually 5. Those are all in a row. I can draw them without lifting my pen up, or finger in this case. I would call this one a pentane. I also want to point out, don't get confused when you see one like this. Again, some people might look at this and say, well, I got a butane because there's 4 in a row. Well, hang on a second. We can actually get 5 in a row if we count up there. So butane, no. It's actually some kind of pentane. Okay, it can bend around. You just want to draw out your longest chain. So go complete sheet 1, check your work, and don't get fooled. Every trick I could think of is on this sheet, so go check it out. Let's continue by looking at some cycloalkanes. We've added the word cyclo in front. Cyclo just means a ring. So this is a ring of a hydrocarbon chain. So a chain becomes a ring. How does that happen? Well, let's do the simplest one here with propane. So straight chain propane. Under certain conditions, you can actually remove those hydrogens on the end. They're going to find each other and they're going to make H2. Well, then this thing's not exactly happy. Those carbons aren't stable. So what they want to do is they actually want to wrap around on itself like that. And they want to form a ring. And there is your simplest hydrocarbon. So let's make a table. So your simplest cycloalkane is, we can't have 1 or 2, you need to at least have 3. So this is the one we just looked at. Now, what I like about this is the condensed drawing, which is a triangle, because that's the shape here, right? That shape there looks like a triangle. By just drawing the triangle, it actually is considered that all of these other hydrogens are there. So as long as you know that there are 2 hydrogens on the ends, you're good to go. We're going to call this one cyclopropane, because it's a propane, but it's a ring of 3. It's a cyclopropane. So when you have 4 carbons going on, it looks a little something like that. You ask yourself, what shape is that? Well, it's a square. And this would be cyclobutane. You can just copy that down. Just draw the square. That's how I would do it. 5 carbons, looks like that, but the shape is a pentagon. It's cyclopentane. And 6, I'm going to stop at 6. We're going to go this high. This is our cyclohexane. There's a lot of chemistry involved with cyclohexane. And when you get 7, 8, or 9, or 10 in a ring, it just gets hard to draw. So I'm going to mostly focus on these versions. So let's do some naming. There's just some slight adjustments we'll make to our naming rules. We probably don't need to come up with a set of rules. So here's our first example. So the first thing you want to do is you don't necessarily worry about the longest chain. You just need to worry about the shape that you've got going on there. And that is a cyclohexane. We do want to number our rings so we get the lowest number possible. And you're always going to have something in the 1 position. The earlier lesson with our straight chains, you'll notice that we never had the number 1 on any example. If you did, something was wrong. But now with these rings, you always have something in the 1. And this one's being symmetrical, so we can actually have probably a couple of different answers. I could call that my first, that my second, and that my third. Or even vice, I could also say this is 1, 2, and 3. Either way, I'm going to get the same answer. So I got a methyl group on the 1 and a methyl group on the 3. So 1, 3 dash dimethyl cyclohexane. All right, what if we do this one here? Another example. So again, we have a cyclohexane. Now we want to number our chain, and again, this one's fairly symmetrical, so we're going to get two answers, both of which could be correct. Let's say that's the first carbon, that's the second carbon, that's the third carbon. That'll work properly. Those will give us our lowest number possible. That's what we're always after. It looks like we've got a methyl group on the 1, a methyl on the 2. The letters are reversed, but still a methyl group. And then this thing here is an ethyl group. So once again, we'll say ethyl goes ahead of methyl. So we have a 3-ethyl and a dash, and then a 1,2 dimethyl. There's your 1,2 dimethyl. Well, frankly, if we had numbered this the other way, if I had said that this is the 1, this is the 2, this is the 3, I'd actually get the same numbers. So I would probably accept either or in terms of names, because they both have the same essential numbers there. I missed a dash. This should be a dash right there. Sorry for me to draw it in. There we go. Dash 2, 3 dimethyl cyclohexane. So those are the same. Final example is just a simple one here. Your ring is once again a cyclohexane, and this group is a methyl group, methyl cyclohexane. Now some people are probably thinking, do I put a 1? Is this a 1? Well, the fact is we could turn this molecule any different direction, and that single group is always in the 1 spot. So it's just methyl cyclohexane no matter how you look at it. Complete sheets 2 and 3 and check your answers.
Organic chemistry. Hydrocarbons. Last time we looked at alkanes with single bonds, and this time we're going to be looking at alkenes with double bonds, and then alkynes with triple bonds. And let's remember that these can come as straight chains or as ringed compounds. So let's proceed with some alkenes. These are compounds that contain a double bond, which would be right there. Any hydrocarbon containing a multibond is also known as an unsaturated hydrocarbon, so alkenes are unsaturated. There needs to be at least 2 carbons present in a molecule for a double bond to occur, meaning you can't have a double bond with methane, something like that. It's got 1 carbon, won't work. So our simplest one is going to look like that, 2 carbons bonded together, and you can put the hydrogens on the ends as well. Once you've drawn your molecule, notice that we now have like a CH2 unit bonded to a CH2 unit. So our condensed formula looks a little different than some of the other condensed formulas. In fact, if you saw that condensed formula, you should say, well, that molecule probably has a multibond because there are fewer hydrogens than there should be. In terms of naming this one, it's got 2 carbons, so there is an eth involved, and since it's an alkene, we put an ene at the end. This is ethene. Well, what do you think about this one? It's got 3 carbons to it, so it must be a prop, and then it's got a double bond right there, so it must be propene. So that is our second simplest alkene. Now here's a little challenge for you. I want you to draw butene. So if you're going to do this, butene has 4, so 4 carbons, so you draw your chain of 4, and you put your double bond probably in that first spot. And that's probably, if I had 30 people do it, probably 25 people would make that version, and there's nothing wrong with it. However, the other 5 people, there's the hydrogens. By the way, the other 5 people would do this, and they'd put their multi-bond in the middle, right there. Now, both answers are correct. Check mark, but they're clearly different. this molecule has a multi-bond right there, and obviously this one's in the middle. So if we name those ones, they would both be butene, but we know they are different. So we need a system of coming up with how to tell them apart. Essentially what we need is we need a number to tell us what bonding spot that multi-bond is in. So in the last section we numbered our carbons 1, 2, 3, 4. But what we're doing now is we are numbering the bonding spots. So this is going to be number 1 bonding spot, that's the second bonding spot, that is the third bonding spot. So we have a multi-bond in the first bonding spot, making this one 1-butene. And if you look over here, that would be a 2-butene. We have 2-butene here. So we have made a discovery, and we've made sort of a discovery in the isomer category. By the way, there is an alternate name for these. So the number can go between the ending and the prefix. So I should mention that because you'll see both versions coming up. I'm more partial to the number out front, but both are correct. What we've discovered is something called a positional isomer. So these are unsaturated hydrocarbons where the multi-bond can appear in different locations on the parent chain. And they cannot occur until butene. So if you remember back to the propene we drew, there would only be one way to do it because it would just kind of be flipped around. So it's in the one spot here, and if you flipped it around, you'd still have it in the one spot. You always want to go with the low, and that's going to be a rule coming up. We always want our multi-bond to be in the lowest position numerically we can. So these are in fact the same, ergo that one does not exist. We would call it propene. We would not call it 1-propene. So let's name and draw all positional isomers of hexene. So how many are we talking? We're talking 6. So you can pause the video now and draw your attempts. Welcome back. Let's take a look at what you might have drawn. So if you're going to do this, you'd probably lay out your 6 carbon chains like that, and you might try it again and again, and then you'd say, okay, back to the first one here. I'm going to put that multi-bond in the first spot. Boom, I have my first one. I've got 1 hexene. Move down to the second example. We're going to put it in the next spot. We're going to call that 2 hexene. And then we're going to jump up to that third one we drew. We're going to put it in the middle spot. And we're going to call it 3 hexene. And then we're going to say, does 4 hexene exist? And the answer is no, it doesn't, because it would just be 2 hexene flipped over, right? It would just be that one flipped over, and you always want your number to be in the lowest possible. So 4 hexene would not exist. And there are all the hydrogens drawn in just to make it correct. Kids forget that. I don't know why. All right, so let's go ahead and name the following. Now we're going to do, it's not really a set of rules because it's just sort of one rule, rules for naming alkenes. We want to name the longest chain containing the multi-bond. Make the multi-bond have the lowest number possible. Okay, so longest chain that contains the multi-bond. Sometimes you can find a long chain. If the multi-bond's not in it, then that you got to default back to this rule. So let's look at this one here. I'm thinking we're going to have our longest chain straight across. 1, 2, 3, 4, 5, 6. So that would be 6. So this is some kind of hexene, and then I've jumped ahead here slightly, and I've numbered the bonding spots as 1, 2. So we have a 2 hexene on the go. Now I'm not going to renumber the chain to get this substitution group the lowest number possible. I'm just going to kind of keep going here. And so I'm going to go back and number our carbons. That was our first carbon, that's our second carbon, that's our third carbon, that is our 4th carbon. So we have a ethyl group on the 4th carbon. So this is a 4-ethyl hexene, hextuene. So there you go. So there's our rule. We got our longest chain, we got the multi-bond to have the lowest value possible, and then we just name the rest of the groups that were there. Okay, so looking at our next example here, I think I'll draw your attention to here. We've got 3 carbons all squashed together, 1, 2, 3. So if we draw our longest chain, or at least attempt to, we've got 3, 4, 5, 6. We actually have 6 carbons right there. Unfortunately, there's no multi-bond in that chain. So your next thought might be, okay, straight across, 1, 2, 3, 4, 5. I've got the multi-bond, but I'm going to say, hang on a second here. Let's not forget we have 3 squashed together. So we have 1, 2, 3, 4, 5, 6. We actually can get 6 carbons in a row, and our multi-bond is contained there. So the multi-bond looks to be in the one spot. We're talking about a hex 1-ene. Now, what's left over here? Well, we've got 2 carbons and 5 hydrogens. That makes an ethyl group. What carbon are they on? Let's see, 1, 2, and 3. So this chain is on the third carbon here. We're talking about a 3-ethyl hex 1-ene. Let's try another example. Oh no, we got a ring here. See this contraption right there? That would be your multi-bond. Now, we want to get our multi-bond to have the lowest number possible. So we want to consider that, but we also want to consider where the substituent groups are. So there's always kind of two ways to name this. This has to be in the first bonding spot. That means this corner carbon here has to be carbon 1, and this one has to be carbon 2, or vice versa. This could be carbon 1, and this could be carbon 2, and the subgroups are what's going to dictate what is actually proper. So it looks like the green version is going to be right, because we'll have our subgroups on the third carbon. I guess if we numbered the other way around, that would be 3, that would be 4, that would be 5 there. So obviously 3 is lower than 5. Okay, so this multi-bond is always in the 1 spot. We've got 5 carbons here. We're going to call this a cyclopentene. What we're missing is the number 1. That number 1 is not necessary because this is always in the 1 spot. So you don't need the 1 in front, in the middle, wherever. It doesn't belong. Once you've got that cyclopentene, that indicates there's a double bond. You just need to know that we've got a couple of propyl groups on the third carbon here. So a 3,3 dipropyl. Ta-da. Well, that's only half the story. Alkynes. Triple bonds are what we're talking about now. And again, a multi-bond is unsaturated, so alkynes can also be considered unsaturated hydrocarbons. There needs to be at least 2 carbons present in a molecule for a triple bond to occur. So the simplest alkyne looks a little something like this. I already named it as ethyne. There you go. It's straight across, and we have our triple bond there. So ethyne. We also have some positional isomers. So these are unsaturated hydrocarbons where the multi-bond can appear in a different position, and they cannot occur until butene. So here's your first one. So this would be a 1-butene, and there would be your second version of it. It would be a 2-butene. Again, remembering carbon wants to form 4 bonds here, so make sure you fill the hydrogens in accordingly. Okay, let's take a look at this example here. There's no hydrogens, which would be wrong. Let's just proceed without it, pretend they are there. So we're going to find our chain, our multi-bond spot first. So 1, 2, 3, it looks like that'll be lowest. It sure would be 3 if I went that way, but then these subgroups would end up having nice high numbers. So I'm going to stick with going left to right in terms of my numbering. And in terms of my carbon, I've got a couple of methyl groups off the second carbon. So back to the green here. We've got 6 in a row. It's in the third spot. It looks like we've got a hex 3-ine. And then we've got a couple of what would appear to be methyl groups if the H3s were written in. So we have a 2,2-dimethyl hex 3-ene. What happens if we get a multi-bond example here? Well, same kind of difference as earlier. We still want to number these to either be 1, 2 or 2, 1. Depends on these groups here. I think my blue numbers should be the best. So we've got 5 in the ring. So this is going to be a cyclopentine. And then my subgroups, we've got alphabetical, we've got a propyl and a nonyl. So nonyl comes first, 4 nonyl, and then 3 propyl cyclopentine. Go ahead and complete worksheets 4 and 5.
In this video, we're going to investigate different kinds of isomers. So in general, isomers are compounds that have the same general formula, but they're different molecules. And we have 3 different types of isomers. So this definition that I've got here right now, this is just sort of our general definition for all 3. And then there's a little something extra that's going to set the 3 apart. So taking a look at the first kind here, we have something called structural isomers. And again, I've put isomers are compounds that have the same general formula but are different molecules. So how are they different in this case? Well, they're different because we are going to connect the carbons differently of the parent chain or the longest chain. And this is going to create different parent chain lengths. So let's take a look at an example here. So let's take a look at drawing C4H14. And I only want in this scenario 4 answers for the structural isomer, but just keep in mind that there are actually 9 answers. So the first answer I would draw would be simply to take this C7H14 and draw out everything as a straight chain. This is our low-lying fruit, if you will. And it gives us this molecule here. You can count it up. There are 7 carbons. And we're going to call that one heptane. Now there's no other version we can draw of 7 straight carbons. You can bend the carbon up here, but it's still going to be a chain of 7 in a row. So no matter how you bend it, we've only got one heptane. So our next goal is going to be to take it one step down from heptane and look at what kind of hexanes can we draw. So I've drawn the first one here, hexane. 1, 2, 3, 4, 5, 6. So there are 6 carbons in a row. There's my hexane. And what I'm going to do is I am going to take a CH3. So in essence, we're kind of removing sort of this end part here, and we're trying to attach it to a different place on our chain. So you can clearly see that right here I've kind of left a space for that CH3 to go. And when we put in that CH3, we now no longer have a heptane. We've got our longest chain of 6. We've got a hexane, and now we have this group here, which is our methyl group on our second carbon. So it's going to make a 2-methyl hexane. So at this point, you should ask yourself, is there any other version of hexane I can make where I just move that methyl group around? And there does happen to be one. And you can see that little notch there in my picture. That's going to be our methyl group. So again, we have 6 in a row, and now this time we have this to be on the third carbon. Hence, we have a 3-methyl hexane. I don't think we can have a 4-methyl hexane because I think that would be exactly the same as 3-methyl hexane, but just flipped over. So then you start to ask yourself, okay, what about pentanes? How many 5-chain ones can I make? So you draw your 5, and then you say, again, I can't put in any methyl groups on the end. Let's start with the second carbon here. And so we can actually put one up and one down. And so again, we have our chain of 5, pentane, and we've got a couple methyls both on the second carbon. So 2,2 dimethyl pentane. As well, too, for more answers, all we're going to do is start to move around these methyl groups. So the other answers to this question would be a 2,3, you're just moving one of the methyl groups over. A 2,4, you're moving it over again. A 3,3, they're both moved to the middle. And a 2-ethyl pentane. And a 3-ethyl pentane. So those would be all of your 9 different answers. And if you drew all of those, they would all have the general formula of C7H14. Now you're probably wondering what happens if okay, these are all pentanes. Are there any butanes? And I put a little note here that if you try to draw a chain of 4 and then try to put a group of 3 off that chain of 4, you're just going to simply recreate one of the previous 9 answers. You think it's got a different name like propylbutane or something like that, but it would just actually be one of the answers that we already have. If you don't believe me, draw it out and find your longest chain and go from there. Second type of isomer is called a positional isomers. So again, compounds with the same general formula. What makes positional isomers different is that we're going to locate the multi-bond, not band, multi-bond in a different spot on our parent chain. So we're going to find that this type of isomer can actually apply to both alkenes and alkynes, unlike our last one that was just dealing with alkenes, at least in that example. So let's name and draw all positional isomers of heptine. So heptine, that's 7 carbons. The Y tells us there is a triple bond in this molecule. So the first thing I'm going to do is draw my 7 carbons and put my multi-bond in the first bonding spot here. So not the first and second carbon, but our first bonding spot. And that's why we're going to call this one 1-heptine. To get a different answer, we're just going to take this multi-bond and move it over to the next place. We're going to have a 2-heptine. So that would be our first bonding spot. That's our second bonding spot. Again, not to be confused with first, second, and third carbons. And then our next answer is going to be 3-heptine. Again, you can see we've moved over one more spot. You're probably wondering, is there a 4-heptine? And the answer would be no. There would be no 4-heptine because it would be the exact same as 3-heptine. It would just be flipped over. But let's not forget, and I find students get excited when I ask this type of question, don't forget to draw the hydrogens in. I know I haven't drawn them in here, so there's some of them. Sorry I didn't take the time to put them all in, but make sure you add all the hydrogens in. On to our last type of isomer, which is called a geometric isomer. Another name would be a stereoisomer. And in fact, we're going to even know these by a different name once we get into this. So again, these are compounds where same formula, but are drawn differently. Now the difference for these ones is that we're going to actually draw this differently in 3 dimensions. And this is weird because on a piece of paper or even on this PowerPoint slide, things are in 2 dimensions. So there are some dotted lines and some little triangles to set these 2 situations apart. And we're going to take a look at how I do these molecules. So let's name and draw 2 different versions of 2-butene or butene. So what I like to do here to set these apart is I actually like to sort of start in the middle of the molecule. So I'm actually starting at this 2 part here. Now butene tells me that there are 4 carbons to a bit of a chain. So really what I've got here is my second and my third carbons that are listed. So what I'm going to do next is I am going to draw a couple of bonds, and I'm going to draw in the rest of my chain. So you'll now notice that we have 1, 2, 3, 4 carbons. In terms of our bonding spot, that's our first, that's our second, and of course that's our third. But we're just interested in this 2 spot here. And I also do like to make sort of a big deal out of the hydrogens like that. Put those pointing down there. So if we had to name this one, oh, actually, you know what? We'll name it in a second here. Let's go on to the other version here. That's going to look pretty much remarkably similar. I'm going to start in the middle. We're going to build up. But what we're going to do here, kids, is we are going to switch that group and that group around. And when we do that, you'll notice we have a hydrogen up top and our methyl group below. It's not even our methyl group. It's just part of our main chain here. In terms of naming these two, they're both 2-butene. But this first one we're going to call cis-2-butene, and the second one we are going to call trans-2-butene. Now, how can we tell those apart? Well, I got a good system for this. So, the carbon chain itself looks a little like this shape here, which in essence is the shape of a U. But if you were to turn a U on its side, it would become a C, and that's the first letter of cis. Over on our other example, we have a sort of a straight line here of carbons this time. And if you just randomly cross the line for no reason and made it into a T, you would have your trans-2-butene. So that's how you can tell cis and trans apart. And by the way, it doesn't necessarily even need to loop up. It could also go down. Or this one could go in this direction. Doesn't really matter. You can flip them around. So let's name and draw 2 geometric isomers of 3-octene. So again, when I go to do this one, I am going to build out. So the C part is always my starting point. Now, first thing I got to think here is that octene is 8. So I have to add 8 octenes to my structure. So what I'm going to do first is I'm going to work on maybe the left side here. I'm going to add 1 CH2 group here, or 1 carbon, and add the hydrogens afterwards, and another one here. Now, why have I done that? Because when I work backwards like this, that's the first bonding spot, that's the second bonding spot, and that's my third bonding spot. And that's what I want. I want a 3-octene. So now that I've got that ready, I just need to add the rest of my carbons in. I already have 4 in line here, which means I need another CH2. That's 5. There's 6. There's 7. And there's my 8th one. And then don't forget about your 2 hydrogens here. But sometimes I'm lazy. And you can write out these 4 carbons and 9 hydrogens. But sometimes I'll just write it like that. So those 2 molecules are the exact same thing. This is not a butyl group here. This is just the chain that I squashed down because I was too lazy. We also have, and we're going to call this one the cis, right? Because this is in our cis formation. So we also have our trans 3-octene. So in essence, this is again going to be the exact same molecule, but what we're going to do is we're going to flip-flop that H and that C4H9. They're going to look like that. And now we have our trans version of our octene. I should also make mention that these hydrogens here on either of these chains are places where we could add some methyl groups or something like that. So it is possible to have a substituent coming off these 2 chains. Got one more question here, which is name and draw 4 structural isomers of C5H10. Now this is different than our earlier question. I think the one I asked earlier was C7H14, which meant it was all single bonds. C5H12 would represent pentane. But what we've done is we have removed 2 hydrogens, meaning we've got at least something with a multibond, and maybe even something with a ring. So let's take a look at some of our answers here, and there are quite a few answers. In fact, there's 12 different answers for this question, and I think I've got 4 here on my slide. So the first ones would be a structural isomer, a pentene. We've got our first answer here is a 1-pentene, and we got our second answer here is a 2-pentene. Now what you can also do is you can also have some substituent groups come off these things. So here we have a 2-methyl-butyonine. So again, you find your longest chain. There's your but part. You got your multibond in the 1 spot, wherever that happens to be. And then you've got this methyl group coming off over here. So there's your methyl part, and there's the 1-butene part. So you could move that methyl group around, or you can even move the multi-bond around to see if you can come up with some different versions of that. There's probably a 2-methyl-butadiene possible. You can also get some rings. So again, here we've got a cyclopentane, and if you count it up, there are 5 carbons and there are 12 hydrogens, so that is C5H10. And then there's actually a bunch of different rings you can make. For instance, you can make a cyclobutane that has a methyl group coming off it, and then a cyclopropane. There's a few different answers in that direction. So this is sort of a different type of question. I did say it was structural. In fact, maybe I could have just said, even left out the word structural and just put isomers down. And then it ends up being a question where we've got alkanes, alkenes, and alkynes, kind of everything rolled into one question.
All right, we're going to look at some physical and chemical properties of hydrocarbons. So let's start with the physical ones. So boiling point is a good place to start. So what I've got here is a little picture that shows the number of carbon atoms. So we're increasing. And we've got temperature, which is increasing in this direction. And you can see that as one is going up, the other is going up as well. So as chain length increases, so does boiling point. And why is this? Well, when you get your longer hydrocarbons with like 7 and 8, what happens is the hydrocarbons are able to sort of interact with each other. So that picture, that's a hydrocarbon. And then his buddy is right there beside him. And remember that when you've got even a molecule that's nonpolar, there could be some London dispersion forces, which causes a little bit of a dipole. And so they are going to have some attractive forces for each other. So the longer the molecule, the more attractive forces they are going to have for each other. One other thing about boiling point too is, and I want to compare isomers. So we've got C5H10. So there are 3 isomers here. We've got pentane, 2-methylbutane, and dimethylpropane. So let's notice with our straight chain alkane that we have a boiling point of 36. Once we start to add these branches in right here, right, it's not straight chain anymore, there's your branch, the boiling point is going down. And then when we have a bunch of branches, our boiling point drops even more. Well, what's going on here is that the more branches you have, the less the intermolecular forces of attraction are going to be for each other. So again, it's like the branch chain ones, they just can't pile on like that last picture, with say we had a second pentane, it would just be able to fit perfectly there. There'd be some attraction between the 2 molecules, and that would take more energy to tear it apart, so you'd have a higher boiling point. Once you start getting these branches, they don't quite lie perfectly together, and so there's a reduction there. Melting point. So melting point is in blue here, and it is got a little jagged, but is steadily going up as well. So as chain length increases, so does melting point. Density. So we've got our chain length increasing here, and look at the numbers. They are steadily going up, almost each and every one. Looks like we do have an exception there, and that's chemistry for you. I find there's always one exception when you're looking at stuff, at least one exception, maybe more. So as chain length increases, so does density. So to summarize our first 3 trends, as the chain lengths increase, all 3 trends increase as well. That should be easy to remember. And lastly, solubility here. So here's our picture. We've got polar water and we have a non-polar cycloalkane here. And you can see there's a division, so they're clearly not mixing. They're immiscible. So hydrocarbons are non-polar. Don't forget that. So they would be immiscible in polar solvents like water. In other words, they do not mix. Immiscible. All right, let's talk about the chemical properties now. Combustion. So all hydrocarbons are flammable and burn readily, and they have a little combustion equation. So you're going to take your fuel, which is your hydrocarbon, and in the presence of oxygen, you light a match. It will make carbon dioxide, water, and energy is going to be produced as well. E for energy. Let's look at creating some balanced equations. So that'll be kind of our first step. Combustion of pentane. Pentane, 5 carbons, 12 hydrogens. So that's your fuel. So let's add our oxygen, let's add our carbon dioxide, and let's add our water. Now it's about balancing. If I was going to balance this one, I'd say, okay, there's 5 carbons there. I probably need a number in front of the carbon dioxide, and it's a 5. Then I'd look at the hydrogen. We've got 6 we have 12 and a 2. Answer is 6. And then it's about counting up your oxygens. Don't forget, we've got oxygen in both molecules here. 5 times 2 gives us 10 oxygens. and 6 times 1 gives us 6. So we actually have 16. So what number multiplied by 2 will give us 16? That should be 8. Now, these don't always balance so nicely. Combustion of hexane kind of looks the same. All I did was add 1 carbon. The equation is the same. Balancing starts off pretty clear. And in terms of our oxygens, we should have 12 there. And now we have 7 here. Plus 7, that equals 19. That's an awkward number. So what times 2 will give us 19? Well, it's actually, we can do a half number here. You can go 9.5. Some people will say then you need to double everything, double all the numbers. By the way, that's a 1 in front of the hexane there. Double all these and you'll have your correct answer, but the half method is fine. So sometimes you'll need a half number there. Substitution reactions. If you play sports, volleyball, soccer, they make substitutions for players, and that's just simply players are switching in and out. And it's a reaction where 2 atoms are switching spots. So we've got a methane and a chlorine. So what's going to happen here is our chlorine, it could be that chlorine, is going to switch with any one of the hydrogens. Let's just pretend those 2 are switching. They're going to switch spots. We're going to have 2 products. We're going to have a chloromethane and we're going to have hydrochloric acid. So when you do a substitution reaction, they're only going to be able to be done on our saturated hydrocarbons. Make note of that. Yeah, and you can only put one of these chlorines or whatever you're putting on at a time, one at a time. The addition reaction, these are going to be for unsaturated, so we're double and triple bonds. And what we're doing is we're adding something across that multi-bond, and the multi-bond's getting reduced. Meaning if you got a triple bond, it's going to get reduced to a double bond, and a double bond will get reduced down to a single bond, kind of one step at a time. And so unsaturated gets converted to saturated. And here's kind of a general version, so you can see that our X has gone to that carbon, and the Y has gone to that carbon, and our double bond is broken. It's down to a single bond. So hydrogenation is the name when hydrogen is added to a molecule. So we've got a propene and we've got a hydrogen. So another way to think about it is it's H with a bond to another H. So you're going to put one H on that side and one on that side. And you get propane. Now this one has a triple bond and it's actually got a 2 in front of the hydrogen, which means there's going to be 2 moles of hydrogen reacted. So it's like having 2 of these H-H things. And the way this one was done, they were obviously, while we're taking a triple down to a single, I might have done this one a little bit differently. I might have made this into a double bond like so, and only used 1 mole, and then added that 2nd mole here, and then gone down to the single bond like that. That's probably the way I would have done it 2 equations. And here's kind of another example of that. So we have a double bond, and you're adding your 2 moles of hydrogen in, and double bonds are all gone. You're down to single, the cyclohexane. Now there's one complicated thing that we have to talk about here. So a hydration reaction adds water across a multi-bond. We need to remember that we've got hydrogen and OH going on here. So again, this molecule here is HOH. So we're going to break the double bond. We're going to have 1 hydrogen go on that side, and the OH is going to go over to that side. And we're going to get that. In terms of naming this one, this would be, pardon my writing here, that would be ethene, that would be water, and then this would be a couple of different ways you could name this one. You could name this one ethanol. That would be one way. You could name it hydroxyethane. I don't know, I like that one personally. Now we're going to look at one interesting case here, and that's, well, what if we could have several possible outcomes? So we've got a propene here, and what we're going to do is we're going to add hydrochloric acid. So really, it's about this chlorine right here, because it could go to 2 spots. It could attach to that carbon, or it could attach to that carbon. So we could have 2 outcomes. We could have a 1-chloropropane where it attaches to the outer carbon, or we could have a 2-chloropropane where it attaches to the inner carbon. Now we need some kind of rule to break the tie. Which is correct? Maybe they're both correct. Well, one's actually more correct. And this is Markovnikov's rule. So the rule states that when you're adding protic acid, HX, to an alkene, the acid hydrogen, and this is the important part here, gets attached to the carbon with more hydrogens on it. So the hydrogen is going to go to the carbon with more hydrogens on it. So if we look here, this carbon has 2 hydrogens, that carbon has 1, and the rule is telling us that our hydrogen is going to go to the carbon that has more. So it's actually going to go to this one. So in fact, it is this result which is more correct. And this one's kind of correct. It's like a minor product. This is the one we go with.
And bonds. All right, so this lesson is going to require some previous knowledge of hydrocarbons. So alkanes, alkenes, alkynes, some expectation that you've already done some work with that. Additionally, we're going to talk about combustion, addition, and substitution reactions. And since we're familiar with a lot of drawings, there's a few other molecules we need to cover first, because these 10 molecules I'm about to show you will appear frequently throughout this lesson, in addition to all the hydrocarbons that we've been learning about. So if you want to just make a little table here, the very first one and the most simple molecule that we need to talk about is hydrogen gas. It's in group 1. It shares 1 valence electron, and so it ends up having a single bond. Now there's a bunch of gases in group 7, including fluorine, that, they're in group 7, they share 1, so they're going to have singular bonds. So the rest of these gases in group 7, so chlorine, single bond, bromine, single bond, and iodine, single bond, all these gases are all going to bond in the same way. So all 5 of the gases on this slide all have single bonds. As we move on, though, they get a little more complex. So we've got oxygen gas. Oxygen's in group 6. It'll share 2 valence electrons to get up to 8, and thus we have a double bond for oxygen gas. Nitrogen gas is in group 5. It'll share 3, so nitrogen gas ends up with a triple bond. Water is a molecule that's going to appear frequently. It's made up of 2 OH bonds, so 2 per molecule. Another common one is ammonia gas, NH3, and this one has all single bonds as well. And lastly, carbon dioxide, and this one has a couple of double bonds. So now that you have all of these written down, they're going to appear throughout our lesson, and the expectation is you can take a look back at this, memorize the bonds, and there you go. That's really what you're going to have to do, is commit these things to memory. So we're going to talk about some exothermic and endothermic reactions here. So during a chemical reaction, the chemical bonds and the reactants are broken and new bonds are formed. So the breaking of bonds requires energy, while the creation of bonds releases energy. So really it's a 2-step process. We've got the energy that's released when we break bonds, and then the second step is the energy needed to create new bonds. So there's 2 steps here. For a chemical reaction like the one described, the total energy in the system and surroundings must be the same, so there's really no net change. This means that the energy must either enter the system from the surroundings or exit the system into the surroundings, and this is where exothermic and endothermic, so exothermic is hot and endothermic is cold, this is where these come into play. So system could be anything like, say, a test tube where you're doing the reaction, and then in which case the surroundings would be the rest of the world. So 2 things are going to happen. Either your system is going to get hot or your system is going to get cold. And we're going to take a look at those 2 scenarios with energy now. So a reaction that produces an excess of heat or thermal energy is known as an exothermic reaction. Heat exits the system. Exit, exit. So in this case, it would feel hot. So this is because the energy required to break the bonds in the reactants is less than the energy produced by product formation. I'm going to show you a picture in a second to better illustrate this. In fact, here it is. So we've got an axis, we've got potential energy, and we've got time. So we've got some reactants in our test tube, and the very first thing that's going to happen, step 1, is that the bonds are going to break and the overall energy in our system increases. A little bit of time is going to pass. Step 2 is going to occur, and that's where bonds are going to form, and we end up with our products here. So if we just consider this to be our system, we actually have less energy in the system. So we started here, and we're ending up here now. We have a difference. We have less energy in our system. So we've got a change in energy. Energy in the system has gone down. And this is what is represented by an exothermic reaction. So this change in energy you feel as heat coming off of the reaction. So energy is released into the surroundings from the system. An endothermic reaction is completely backwards, or opposite, I should say. We have the same graph, if you will. We have our reactants. That's all the same. We break bonds. We reform bonds, except this time our products are higher up. We have more energy in the system. We started here. If you want, you could assign any number to this. Say it's 100, and now we're up at products. Say that's 150. We've increased in energy. We have a change in energy that is increased. Now, when you probably think that, you're hearing, oh, increase, it gets hot. No, this is, again, we are talking about a system here. And what's happened to the system is it's actually taken in energy or heat from the surroundings. That's how this has gone up. It's taken in energy. And when it takes in energy, we feel that as being cold because we are in the surroundings. So there's a quick breakdown of endothermic and exothermic reactions. Now we're going to talk a little bit about delta H, and it's a measure of this total internal energy of a substance during a chemical reaction. The bonds in the reactants must break first, and for bonds to be broken, energy must be added, which is in fact an endothermic process, right? And we just talked about that on the last slide. We feel energy as cold. We feel cold in that situation. This results in energy term having a positive sign. So we're going to have to associate endothermic reactions with a positive delta H. When we make bonds, when we make new bonds, this releases energy, which is an exothermic process. So whenever we release energy, releasing gets hot. Thus, the energy term associated with this step is negative because the system has lost heat. That's where the negative is coming from. So what we're going to do here is we're going to take our delta H and we're going to take the sum of the energy required to break the old bonds. We're going to find these values on a table I'm about to show you. And we're going to subtract off the sum of the energy released in the formation of the new bonds. And there's probably a simpler way to write this. This is our energy required subtracted by our energy released. Now here's the table I mentioned. I will try to link this through Google Docs in the description. If not, here it is. These are the values I'm going to be using. You can always Google them. They should be approximately the same. We've got it broken down into elements, and then we've got kilojoules per mole here for each of these terms. Notice down here we have some multi-bonds. We'll be using lots of those ones as well. So let's apply these to a question. So I want you to prove the combustion of pentane is exothermic. We know combustion is always exothermic, so what I want to do here is I want to prove it mathematically. So first thing we're going to need to do is remember that our combustion equation is a fuel, which is going to be our hydrocarbon. It's going to be our pentane. We add that to oxygen gas. In the presence of oxygen gas, we're going to make water, carbon dioxide, and we're going to numerically figure out what the energy term is. It should be on this side. So, first things first is we write the formula of pentane. If you're not sure the formula of pentane, draw pentane out. Count up how many hydrogens, etc., and carbons there are. And then you can just write that formula down there. So C5H12. Once we have that, we're going to need to balance this equation. There's a quick balance. Next step is we're going to need to draw out all these molecules. I know I already talked about drawing pentane. Well, there it is again. So I've drawn out pentane. Now, I'm going to have to draw out 8 oxygen gases. Remember early on, we drew oxygen with a double bond. So we have 8 of these double bonded oxygens to deal with. Those are going to represent our reactants, right? Reactants are on the left side of our arrow. All right, and on the other side, we're going to have our products. So our products are made up of 6 H2Os and 5 carbon dioxides. So these are our products. Now we need to kind of further dissect this because pentane has a couple of different types of bonds, and water and carbon dioxide have multiple bonds as well. So when I'm looking at this pentane, first thing I want to do is I want to see how many carbon-carbon bonds we actually have. So if you just want to count them, there's the first one, there's the second one, there's the third one, there's the fourth one. So this first molecule, pentane, has 4 carbon-carbon bonds to it. Now, it also has a secondary bond. It also has carbon-hydrogen bonds. So how many are there? Well, since there are 12 hydrogens, there need to be 12 hydrogen-carbon bonds. Those are all the types of bonds we have in this first molecule. In the other questions, you might come up with a molecule that has a triple bond, and then maybe a couple of single bonds. That means that your very first thing you do might have more than 2 types of bonds. It could have up to 3 or even 4. So just be aware of that. Now, as we get over to the oxygen gas, there are 8 of them, and there's really no way to simplify this oxygen gas. It's just one double bond per molecule. So we have 8 of them, so there's 8 of these double bonded oxygens. Let's put the arrow in. Now, when it comes to this water, H2O, we've got oxygen-hydrogen bonds. There are 1, 2 per molecule. You see that? 1, 2. 2 per molecule. We have 6 molecules in total. 2 times 6 is 12. There are 12 OH bonds present here. The same idea applies over here to the carbon dioxide, where we have a couple double bonds. 1 there, 1 there. So we have 2 per molecule, 5 molecules in total. 2 times 5 gives us 10 of these things. Next step is you're just going to go to that table that I mentioned earlier, which is there. And we're going to start to fill the bonds in, or fill the terms in. The first one here is a carbon-carbon bond, which is right there. I can read it. It's 346, so I'm going to put that one in. Then we've got a hydrogen-carbon bond. That one is 338, and we have 8 of those double bonds. Remember, the double bonds are right there. In a second, we're going to total up mathematically what all those are equal to. So 4 times 347 plus 12 plus yada yada. We're going to add those up in a moment, but we'll deal with the other side here, where we have 12 of these OH bonds. OH is worth 460. And then we have 10 of the OC bonds, and those are worth 745. So back to the math here. We want to figure out how much energy the reactants, the energy total of the reactants, and that's 9428. If we go over to the energy that it takes our products to form, we get 1297. Now, we do have this equation here. This will help us figure out if this thing's positive or negative. So we're going to take our equation, or our energy required, and subtract off our energy released. And that's going to be equal to minus 3542 kilojoules per mole. Another way to spot this is just to say that, again, if that's our arrow, we've got that number and we've got that number. Well, it should probably be pretty clear that, this side of our equation here, we've got this much of a difference. So it's like saying we have 3542 on the right side, because 12,000 is bigger than 9,000. So we could represent this here using our potential energy diagram. I'm just putting the numbers in. Again, it appears like we've got more energy, but energy again has been released to the system with that amount of energy being released. And we want to write our equation finally like so. And since it was exothermic, we need to add that number over on this side. Now, I keep it as positive. It's positive on this side because it was a reactant. So there's sort of 2 ways to look at this. If I ask for the delta H and the delta H is a negative value, you need to know that is exothermic. We can sort of eliminate that negative simply by writing it on the correct side of our equation as one of our products. Let's take a look at another example where we get something that's endothermic. So determine if the decomposition of water is exo or endo. We don't know. Some of these, like combustion, are always exothermic. This one isn't, well, I don't know. It could be either. So first thing we're going to have to do is write an equation, write a balanced equation. After that, we're going to have to sort of dissect this and say, yeah, we have 2 water molecules, and we've got 2 of these hydrogens. Those have single bonds, and then we've got that oxygen double bond. And then we got to simplify this one a little bit because it has a couple of OH bonds per molecule. 2 times 2 gives us 4 of these OHs. So there's the 4 OHs there. And then these are already simplified, so we just rewrote them here. Table of values here for our terms. So there are all of those values. You can double check them on the table if you so desire to. I've gone ahead and I've added this one up. And hopefully you can see that we have a bigger number on this side. And it should be bigger by 470 kilojoules per mole. So this is, in fact, the value we need to sort of drive this equation. This amount of energy is coming from our surroundings and is going into our system. So we can subtract them here, and now we get a positive value. So that should tell you that when we have more energy on the left side of our equation, we get a positive value for delta H. Here's our diagram. There's our change in energy. And this is endothermic. I like to finish these off by writing my equation and putting that value as one of our reactants. Again, notice in our equations, if you remember back to the earlier slide, both I write as positive values when they're written in an equation. When we're talking about a delta H with a positive value, that means that we're talking about an endothermic term. And that wraps up that.
This is going to be a two-part lesson. Firstly, we are looking at heat capacity. So all objects naturally resist a change in heat. Some objects are obviously better than others at resisting this heat change. So as an example, it takes 4.184 joules, this is kind of a magic number, of energy to raise 1 gram of water by 1 degree Celsius. Again, it might be hard to picture that. We'll come to some examples that'll help put that into perspective. Okay, so talking about heat capacity. So objects that are good at resisting a change in heat are said to have a high heat capacity and will remain cool. It almost seems backwards for a second until you think about it. So there are a few objects that have high particular heat capacities, or high heat capacities, and so they will remain cool when a lot of heat is applied to them. The opposite, objects that are bad at resisting heat changes, they heat up quickly and they have low heat capacities. And like all of these things, you apply heat to them, they will seem rather hot. So an example here, on a hot sunny day, would you prefer to sit on a bench made of wood or a bench made of metal? And I need you to consider heat capacity in your answer. So thinking about this, if you think about the bench made of metal, it's got a low heat capacity, so it'll be really hot. That says hot. And the bench made of wood has a high heat capacity, so it'll seem rather cool. So that would be the obvious answer. So the bench made of wood, because it would resist the heat change. So that is heat capacity. Now we're going to look at specific heat capacity. We're adding one extra thing to our definition. It is represented by the letter C. So it's the amount of energy it takes to raise 1 gram of water by 1 degree Celsius. Now it's got a rather wild unit here. It's measured in joules divided by grams multiplied by degrees Celsius. So it'll probably more typically look like that. Now here is a table. So I do have one, table 2 is provided somewhere on the website, or you can just simply Google these values. Now they should be, you know, rather consistent. I mean, there's probably a slight variation depending on the source you're looking at. But there are some values now. And again, just to put this into perspective, these two are rather close to each other, water and iron. And really what it's saying is that, you know, water's value for specific heat is about 10 times bigger, right? It's about 10 times larger than its iron friend here. So that means it would resist a change in temperature like 10 times as well. So iron would heat up a lot faster than a sample of water. So we have an equation to help us calculate this. Q equals mc delta T. So to define all our variables, Q is energy that is measured in joules. M is mass that needs to be measured in grams. If you have something in kilograms, you need to convert. C is the specific heat capacity, the aforementioned one. And we have a delta T, which is equal to our second temperature minus our first temperature. I've never really been a big fan of that. I prefer more to think of it as our final temperature minus our initial temperature. The reason I like that is because you can't always depend on the question to give the values T1 and T2 in that order. Perhaps even in a lab, you might just make more sense for it to be T final and T initial. And of course, these are measured in degrees Celsius. Now, the kicker is they can be either positive or negative. So energy can be released to the surroundings or taken in from the surroundings, one or the other. So let's do a couple of examples before you get to work here. So let's determine the energy required to raise 100 grams of water by 10 degrees Celsius. So there are your 4 values. The question's asking us to determine the energy. It's given our 100 grams of water, because that's what's going to be undergoing the temperature change. So you need to look up the specific heat capacity of water at this time. You might remember it from an earlier slide as 4.184, and it does have a crazy unit, but let's leave that off. Now, with our change in temperature, this question's already given you the change in temperature. There's no 2 values, there's only 1, so it's already been done for you. So then it's just a matter of writing down the equation, filling in the values, and coming up with an answer. Now this is energy, and so it will be measured in joules. So that's about as simple as these questions get. Let's make them a little bit harder. So we have a 100 gram sample of water is sitting at 20 degrees Celsius. Determine the energy required to reduce the temperature of the water to 15. So we have a mass here, and we have two temperatures. So it's initially sitting here, so that's our T initial. Its final temperature is 15 degrees Celsius. So let's go ahead and plug in our numbers. We have a mass of 100. Again, our specific heat capacity water, 4.184. And now we're going to subtract our two temperatures. So once you get them in the right order, it's 15 minus 20, which actually gives you -5. I think that makes sense. The sample is cooling off, isn't it? So we'll write our equation, we'll plug our values in, and when we do that, we actually get a negative energy value. And just to be cool, we'll convert that to kilojoules, because that's going to come up in a little bit here. So there you go. So this example is just to show you that you can have negative values, and that is absolutely fine. A metallurgist is working with 10-gram samples of gold and silver. Determine which metal reaches the highest temperature when 100 joules of energy is applied to both samples. So there's our formula, but this question is asking us about a temperature change. So we actually have to rearrange your equation. So there's a couple of different ways you can rearrange this one. So for gold, we've got our equation. Now we've got our 100 joules there. Here we have a 10-gram sample of the gold. Normally these are in water, but this one's just sitting out, pretend. And this value I had to Google, so I just Googled specific heat capacity for gold, and the answer came up. And when you do the computation, you get 76.92 degrees Celsius. Continuing for silver, same equation. The only thing that changes is my specific heat capacity, which I didn't seem to type in properly. There is 0.237. And when you do that computation, you get 42.2. So determine which metal reaches the highest temperature. That would be our gold. It gets the hottest because I guess it has the lowest specific heat capacity. So there are a few questions where you may have to get into some algebra because there's maybe they'll give you an initial temperature and asking for a final temperature. And there's also some questions in the homework where you're going to have to figure out what metal it's talking about. So you're going to have to calculate the heat capacity and then compare it to known values and see which metal you're talking about. So go get that done. We're going to be looking at a couple of things in this section. We're going to be looking at calorimetry, energy transfer, and molar enthalpy. We'll get to that in a little bit. Let's talk about what a calorimeter is. It's simply a device that is used to measure a heat change. So essentially it's just a well-insulated chamber like a thermos that can hold water, and that water is what's going to absorb the heat change. And there's also a thermometer there to measure the heat change. So there's a couple of examples here. This is your classic styrofoam or coffee cup calorimeter, and then these ones are that's a bomb calorimeter. Those are your big boys right there. So there are two types of calorimeters. I mean, there's only one type, but it's the assumptions that we use that set them apart. Firstly, we've got a simple calorimeter. So with this, we assume that the water is the device that absorbs all the heat of the reaction. We assume the calorimeter absorbs no heat, and we assume no heat is lost to the surroundings. Probably the coffee cup calorimeter you saw on the previous page is probably the closest thing we've got to a simple calorimeter, because the styrofoam is really not going to undergo a heat change. So if you think back to all the questions that you did in the first part of 5.2, those would have been considered in a simple calorimeter. The calorimeter wasn't undergoing heat change. So the complex calorimeter, we assume all parts of the device absorb heat. So if it's made of metal, the metal is going to warm up or cool down. And we assume all parts of the device have the same initial and final temperatures as the water. So we've got this equation that we became familiar with in the earlier section, but we actually need to do it twice because we have water that's undergoing a heat change and probably the device itself. So here's a question. A steel calorimeter with a mass of 322 grams is filled with 225 mils of water. Now we do want to work in grams, but hopefully you remember that 1 mil of water is equal to 1 gram. So technically it's 225 grams. The starting temperature of the device in the water is 10.6 degrees, and we have 1.02 grams of ethanol that gets burned, and our temperature rises dramatically. So we've definitely got an exothermic reaction. So firstly, let's calculate the heat change here. So I just went ahead and took the water numbers. There's our mass of the water, our specific heat capacity of water, and our temperature change. And then I repeated with the mass of the device. the specific heat capacity. So instead it was steel, so a quick little Google search yielded that value, and then the same temperature change. Remember we said the temp change will be the same for the water and the device. Plug your values in, and you get about 30,000 joules or 30.11 kilojoules. Now we have to be careful here because this is an exothermic reaction. And what we've learned, or are currently learning, is that anytime we have an exothermic reaction, our answer is in fact negative. Exothermic reactions have negative values. And this is the case where we just have to rationalize this one. Our answer came out to be positive, but really our system has lost the energy, the surroundings is warmed up, and really we have to focus on the system. So we end up with a negative value there. So next thing we can do is something called the heat of combustion. The key part here is it's in joules per gram. So there is our C for combustion. We're going to see a little bit more about this in a second. And there's our values. Now we're taking the mass of the sample here. And again, well, I included the negative up here, so this answer gets to be negative as well. So again, it's a fairly large answer. Now, one other thing, we're going to continue on with the idea of enthalpy. What's the enthalpy change here? So our enthalpy change, it's actually, I guess I forgot to put it here, it's in kilojoules per mole. So we're going to have to find the moles. We're going to have to find the moles of ethanol. So I took the liberty of doing that. This may seem familiar back in grade 11. There's your molar mass. Cancel, cancel. And we end up with 0.22 moles. So simply what we're after here is and there's our enthalpy change, and the R stands for the reaction. We're just going to divide those two numbers, and we get our answer in kilojoules per mole. So let's talk more about this enthalpy idea. So every substance undergoing a chemical or physical change contains a certain amount of thermal energy. The total amount of thermal energy is known as enthalpy, or H. So the energy change that occurs in a system during a reaction is called the enthalpy change, or delta H. So this may seem a little odd at first. So what we're talking about here is the enthalpy change of the system, and what we've done is we put the absolute values around the energy of the system. We have to focus on something here. So we're focusing in on the system, and we can always end up with a positive value with the absolutes, but we have to realize that in exothermic reactions, our enthalpy is going to be negative. And when it's endothermic, our answer is going to be positive. Let us guide that. If you can remember this little thing here, then all this other stuff will sort of just kind of fall into place. So what we're going to be doing here is we're actually going to be taking the enthalpy of our products and subtracting off the value of our reactants. So when the products of a reaction have a greater enthalpy than the reactants, delta H will be positive. And this is endothermic. Okay, this is what I was just talking about here. And then the opposite for the exothermic. Exothermic has negative. And so this is, of course, saying that heat is released into the surroundings. Again, you got to look at it from one perspective. Either you're looking at it perspective of the surroundings, or you're looking at it from the perspective of the system. And so we're looking at the system here. And so system in exothermic is losing energy. Okay, it's going into the surroundings. It seems hot. And then the opposite for endothermic. And then here's these values again just written. So when your delta H is greater than 0, it's endo, and when it's less than 0, it's exothermic. So here's just an example from the book. You've got a reaction here. This is an exothermic reaction, so your heat is dropping. So the energy of the system has gone down, where the energy of the surroundings has gone up. So the surroundings would have a plus value and the system would have a negative value. But again, we can only look at it from one perspective, and our choice is going to be from the system's perspective. So let's talk about the molar enthalpy. Notice I put a little X here because X could be a whole bunch of things. So enthalpy changes involve 1 mole of a substance. X stands for the number of enthalpy changes associated with a phase change. And all these phase changes here have different values. So for instance, here's water. It starts as ice and it ends up as steam. So what's happening here on our straight line portions, so from here to here, we would have one particular delta H value. So this would be like your delta H melting. Now you can have a whole bunch of different things here. So this would be the melting one. We get up here, we've got water, so this one would be a delta H, and this would be like vaporization. All right, so there's even more. You can even reverse these, right? Because you could say you could have the graph going backwards, and instead you'd have the enthalpy of condensation, or the enthalpy of freezing. So there's a whole bunch of these things. They all kind of sort of play out the same though, but they do have different values. So you start looking these things up on the internet, you're going to find they get different values for water. It's really all depends where the question is taking place. So here's an example, and these are just types of molar enthalpy changes. So we've got the delta R there. So there's solution, combustion, vaporization, formation, neutralization. So there could be a whole bunch of different letters here. So molar enthalpy results from simply dividing the enthalpy change by the number of moles present. So this little equation will be nice to use in a moment. We're going to be looking up values for this and then solving for our delta H of the system. Okay, so in this one, we are going to determine the enthalpy change if 100 grams of water vaporizes. So this vaporization term we can actually Google and look up on the internet, and there it is. So what we're after just the enthalpy change when this happens. That was a delta, by the way. That's not a good-looking delta, but that's what we're trying to solve for here. So old school style, we're just finding the moles of water. So you can do that quickly here. We get 5.5. Our grams cancel with our grams there. We're left with moles. So there's our general equation, but what we want to do is we want to rearrange this for the vaporization. So notice I just changed the X here into the vaporization. We're rearranging now at this point, and all we're taking is we're just taking the N from this side and cross multiplying it up so it's right there. And then we're just putting in our values. So there's our mole term and the 40 kilojoules per mole. The moles will cancel out, so your final answer is going to be in kilojoules. So there you go. So representing molar enthalpy changes. So there's a couple of different ways to do this. So one way is writing an equation. So let's do it for the synthesis of water, and this it's an exothermic process, so we have a 285 kilojoule result there. There's a different way to write this, and because it's exothermic, our delta H is going to be negative. I've tried to establish that already in this lesson. Now you can also do this with a potential energy diagram. I think we saw these earlier, and so what you do if it's exothermic is you write your reactants right there. There's a drop in energy for the system, and there are your products. And once again, you'll notice that this was represented with a negative value. If this were endothermic, we'd switch it around and this value would be positive.